Imagine seeing a shark move through a dark tank. The nose is blunt. The dorsal fin cuts above the body. The tail sweeps from side to side. For a few seconds, the shape is familiar enough that your brain fills in the rest. Then it turns, pauses in the water, and holds position with a precision that a real shark never would. There is no animal inside this silhouette. There is a machine. It is called the BS-500, a shark-shaped biomimetic underwater robot built by China's Boya Gongdao. Public specifications describe a machine about 1.85 meters long, weighing roughly 50 kilograms, with a maximum working depth of 300 meters. But those numbers are not the interesting part. The interesting part is the choice that defines the entire machine. Instead of treating the ocean like air and simply adding propellers, the BS-500 tries to borrow the movement logic of a fish. That creates a difficult engineering question. How do you take the shape and motion of a shark, preserve the advantages that make that shape useful underwater, and turn it into a controllable robot carrying electronics, navigation hardware, power, and mission equipment? The answer begins before there is anything that looks like a shark. A conventional underwater robot can be designed around obvious hardware. Thrusters go here, pressure housings go there. A frame carries the equipment, a camera looks forward. Biomimetic design changes that relationship. The outer shape is no longer decoration around the machine. The shape is part of the propulsion system. Boya Gongdao says its biomimetic series grew from more than a decade of research associated with Peking University's engineering work. The company describes the family as using high-speed biomimetic drive systems and central pattern generator, or CPG, control algorithms. In simple terms, a CPG produces coordinated rhythmic commands. Instead of ordering the tail through a long list of isolated positions, the controller can generate a repeating motion pattern that behaves more like swimming. That means the first major manufacturing problem is geometric. The finished robot must still read as one continuous animal-like body. But underneath that body are rigid structures, moving joints, sealed electronics, wiring paths, and interfaces that cannot all move together. The public record does not reveal the exact BS-500 shell materials, internal frame, seal geometry, or factory tooling. Those details matter, so they should not be invented. What is visible is the engineering boundary. A comparatively rigid forward and middle body must transition into a tail section that can move repeatedly while the rest of the machine maintains its form. Its size also changes the way the engineering reads. At 1.85 meters, the BS-500 is not a palm-sized robotic fish and not a massive long-range submarine. It is close to human scale. At around 50 kilograms, it is heavy enough to require deliberate handling, support, and launch preparation, yet compact enough to appear in tanks, exhibitions, and controlled demonstrations without the infrastructure demanded by much larger unmanned underwater vehicles. That middle ground is useful. It lets engineers test a realistic integrated vehicle while keeping the platform small enough for repeated retrieval, adjustment, accessory changes, and another run through the water. That tail is the first real payoff. Boya Gongdao identifies biomimetic tail-fin propulsion as the BS-500's power source. Instead of a visible rear propeller doing all of the work, thrust is created through the oscillating tail. The design goal is not to reproduce every muscle in a shark. It is to reproduce enough of the motion pattern to push water efficiently, while keeping the robot controllable. Now, another problem appears. A tail that produces forward thrust also produces forces that try to yaw and disturb the vehicle. Every change in sweep affects the water around the body. If the control system simply commands more tail motion, the robot does not automatically go where you want. The motion has to be coordinated with the vehicle's attitude, speed, buoyancy, and navigation estimate. This is where the shark shape becomes a control problem. The company's product material says the BS-500 can hover at a fixed point in still water, operate by long-range wireless control, and follow a preset route autonomously. Those are very different behaviors. Cruising rewards smooth, repeated propulsion. Hovering demands that the system stop wandering. Autonomous travel requires the robot to know where it is trying to go, even when no person is continuously steering it. Boya Gongdao also lists fiber-optic inertial navigation on the BS-500. An inertial navigation system watches motion and orientation through onboard sensors rather than depending entirely on an external visual reference. Underwater, that matters. Satellite navigation signals do not simply travel through seawater to a submerged vehicle the way they reach a car or aircraft at the surface. So the robot's visible movement is only the outer layer. Inside, the control system has to translate a route into body motion, translate body motion into tail commands, and continuously compare the expected movement with what the navigation system senses. This is the point where a shark-shaped shell becomes an autonomous platform. And it is also where assembly becomes more than fitting body panels together. Power, control electronics, navigation, communications, actuators, and the moving tail all have to become one system. The manufacturer does not publish a complete BS-500 production line sequence, so we cannot honestly describe an exact secret assembly line. But we can follow the verified integration logic. The machine has to move, sense, communicate, carry its programmed behavior, and survive underwater as one sealed product. The next constraint is configuration. Boya Gongdao markets the BS-500 as a standard product that can be customized. The company lists multiple accessories that can be fitted to the platform. That changes how you should think about the robot. The shark body is not necessarily the mission by itself. It is a mobile carrier whose value depends on what the operator needs it to sense, inspect, or demonstrate. If you enjoy documentaries that separate the real engineering from the dramatic claims, subscribe to Modus Assembly. The most revealing part of this machine is still ahead, proving that the shark can do more than look convincing. Once integration is complete, water becomes the factory's most unforgiving inspection tool. On a bench, a moving tail can look smooth. In a tank, the entire vehicle responds. If the robot is poorly trimmed, it rises or sinks. If the propulsion rhythm is unbalanced, it can wander. If the control response is too slow, a commanded turn becomes an arc. If the navigation estimate and the physical motion disagree, an autonomous route can drift away from the path it was supposed to follow. The BS-500's advertised ability to hold position therefore matters more than it first appears. A fixed hover is a compact test of the whole system. Propulsion, buoyancy, attitude control, sensing, and software all have to cooperate closely enough that the machine stops behaving like a free-swimming object and starts behaving like a controlled robot. Then comes route following. A preset autonomous cruise changes the question from, can the tail move? To, can the complete vehicle turn repeated tail motion into predictable travel? A camera can show the answer in the water. A path graphic can show it from above. The same test can reveal whether the shark shape is merely cosmetic or whether the mechanical and control architecture actually work together. Public reporting from the 2024 Beijing Military Technology Exhibition adds another scale marker. It reported a maximum working depth of 300 meters for the BS-500. That figure should not be confused with a verified combat range or endurance claim. It is a working depth specification, but depth still changes the engineering environment. Because every meter adds pressure to housings, interfaces, seals, and anything that must keep water away from electronics. The deeper point is that biomimicry does not remove conventional underwater engineering problems. It adds another layer to them. A shark-like body may offer a different propulsion approach and a visually unobtrusive form, but batteries still need protection. Electronics still need dry volume or appropriate pressure tolerance. Moving interfaces still have to survive repeated cycles. Navigation still has to remain useful. A beautiful silhouette does not excuse weak engineering. That is why the BS-500 is more interesting as a manufacturing story than as a futuristic creature. The company itself places the product in both national defense and science and education application categories. Broader reporting on Boya Gongdao says its biomimetic and underwater control technologies can support civilian observation and exploration as well as defense-related work. But there is an important line here. Public sources establish defense relevance. They do not establish a specific BS-500 combat deployment, secret mission, or classified payload. That distinction matters, because the machine is strange enough without adding fiction. The more credible strategic idea is simpler. Underwater robots are valuable when they can enter places that are difficult, expensive, or risky for people to inspect continuously. A biomimetic platform adds another design option. Instead of forcing every mission into a boxy frame with exposed thrusters, engineers can package sensing and autonomy inside a body whose movement is inspired by an animal already optimized by evolution for traveling through water. Boya Gongdao has been working in this field since 2015. Its current company material describes a broader portfolio that includes biomimetic robots, conventional remotely operated vehicles, unmanned surface craft, and other marine equipment. That wider portfolio matters because the BS-500 is not an isolated novelty. It sits inside a larger attempt to make underwater machines more autonomous, more specialized, and easier to configure around different tasks. And that brings us back to the first image. A dark shape moves through the water. At first, you see the dorsal fin and the tail. You see a shark. Then you notice the motion is too deliberate. It stops. It holds its place. It turns on command. Somewhere inside that animal-like body, navigation sensors are estimating motion. Control software is generating a rhythm, and an actuator is turning that rhythm into the sweep of a tail. That is the real engineering achievement of the BS-500. It is not that China built a robot that looks like a shark. Looking like a shark is the easy part. The harder problem is making the shape useful, building a body around moving propulsion, keeping the electronics protected, integrating navigation and control, tuning the vehicle until it can hover and cruise, and doing all of that without losing the biomimetic behavior that justified the design in the first place. The central question was how a shark-inspired form becomes a controllable underwater machine. The answer is integration. The tail. Body, navigation, control system, power, accessories, and testing cannot be treated as separate tricks. They have to work as one physical system. And when they do, the moment that matters is not when the robot looks most like a shark. It is when it stops looking like a display model and starts behaving like a machine that knows where it is going. For more evidence-driven documentaries on how unusual machines are actually engineered and built, subscribe to Modus Assembly.